All right, we are going to do something a bit different. We're not. I took away the camera showing me because seeing my ugly mug was a little bit too distracting. So let's just start with answering. What is the decimal equivalent of these particular binary numbers? 10, 111, 10, 110, 110 10 and then 1010 and all ones and 1 0 0 0 0 0 0 1 1. And we can see that if we take 10 1 11 and position them so that they are matching the magic numbers here, we will see that we add 16, we add 4, we add 2 and then 1, and we get 23. And then if we say 110 10, we add 16, we add 8, we don't add 4, we add 2, but we don't add 1. So we have, because we match it up as 11010, so we add 16, 8, and then 2. That's going to be 26. You can correct me if I'm wrong, or you can look it up yourself on Google. You can just Google an online calculator. And when you do the exercises, of course, for me, you're going to be showing your work to make sure you're using this method. But in real life, there's nothing wrong with using an online calculator. But academic, I'm going to need you to set up the problem so you see, so I understand you're looking at it how I taught you, if that makes sense. Here we're having 34, so that's going to be 1 plus 2. That's going to be 34. 32 plus, did I say 1? I meant 32 plus 2 because that's a 1, so 32 drops down. Everything else is a 0, and 2 drops down because that's a 1. So it's 32 plus 2 is 34. 1, 1, all, 4 ones, that's 1, 1, 1, 1, 1, 1, 1. And that's going to be, because they're all ones, you're simply adding 128 plus 64 plus 32 all the way down the line. And that's going to be 255. And then finally 1, and then all zeros except the last 2 are number 1. So we have 128 plus 3 plus 2. So that's 128 plus 2 plus 1. So it's 128 plus essentially 3. And that's going to be 131. This is an alternative way to do it, and that's fine. Now, binary to decimal is more of an interesting thing. So it's basically an algorithm. So first, we compare to each, successive magic number. Like this. And we ask ourselves, is it same size or smaller? And if yes, use it. If not, move on to the next. So let's take a look. 80. Is that bigger or smaller than, is that bigger or smaller? I'm sorry. Is 80 is 128? Another way to look at it is 80 smaller or equal to 128? If the answer is no, we assign a 0 and we move on to the next magic number. And I'll even mark it up. So 80 is not greater than or equal to 128. So we'll assign it a 0 and just cross it off, and then we'll take 80 and then we'll bounce to the next one. Now, because 64 is lower than or equal to 80, we will use it, and instead of a 0, we'll put a 1. And when I say use it, that means we subtract 64 from 80, and we're left with the remainder of 16. So we carry over the remainder, which is 16, to here. And then we ask ourselves, is 16 lower than, or is 32 lower than or equal to 16? The answer is no. We'll assign a 0. We bounce it, and we move on to the next one. Is 16 lower than or equal to the remainder 16? The answer is yes, and the answer is 1. And now the remainder is 0, so we just carry it over to the end. Here we have 65, and we ask ourselves, is 128 the same or lower than 65? The answer is no, and we assign 0. So we bounce 65 to here, and then is 64 lower than or equal to 65? The answer is yes. We assign it a value of 1, and then we say 60. We use it. Use it is taking and subtracting 64 from 65, which is remainder of 1. I'll just say R1, remainder of 1, and then we just apply it to this, and this is going to be bounced all the way to the end, and so we wind up with 1 all the way here. So 65 is equal to 0, 1, and then 0, 0, 0, 0, 0, 0, 0, and then 1. And we can check it easily, because if the binary of 1, 0, 1, 0, 0, 0, 0, 0, 1 is going to be 64 plus 1 is 65. Okay, so a binary to decimal is a little bit more tricky, but if you utilize that algorithm enough, it'll be easier for you. Okay, and hexadecimal, which is base 16. So base 16 only uses the digits 0 through 9 and A through F. And hexadecimal is what we call a compact representation of binary. So here is an example. Binary is base 2, decimal is base 10, hex is base 16. So the first 8 of hexadecimal is 0 through 7. So 0 being the first instance and 7 being the 8th instance, as you can see. So 0, the decimal version of 0 is 0. Decimal version of the hex 1 is just 1. So all these carry over. So I didn't even bother writing their decimal equivalent. Now, the only time it gets catchy is because hexadecimal is base 16, but it's one digit. That is the key. Hex is 1 digit. So how can you represent, for example, the number 10 using 1 digit? So you go from 8, 9, and instead of saying 10, you simply go and you move over to Roman alpha symbols, which is A. So instead of 10 being 10, 10 is A, because it's hexadecimal supposed to represent ones and zeros in terms of 1 digit. 1 single digit, because hexadecimal is fake. It's only a representation of zeros and ones. It is only a compact representation of binary, so it's fake. So in other words, instead of saying 10, they have to say something like A. They didn't have to say A, but it is logically, if you all it is a representation, then you can call it A. 11 is B, 12 is C, 13 is D. So the question might be, okay, if that's the case, how can we convert, for example, binary to hexadecimal? Well, we can use the binary to, I guess you could say, the decimal equivalent, and then adapt that to hexadecimal. So, for example, let's take 10110011. Okay, so the first thing we want to do is break binary into what we call nuggets, meaning a chunk of 4 bits. So 10110011 becomes, breaking that up, if we broke it up here, that becomes 1011, and then 0011. Okay, now 1011, if we compare this to, for example, this, using the magic numbers 1011, that means we add 1 and the 2, but not the 4, and just the 8. So it's going to be 8 plus 3 is going to be 11. Here, let me go back here. That is, I guess, one more. Okay, that's going to be 11. But 11 is just 11 in decimal. What it is in hexadecimal, we have to go to our chart. We can see hexadecimal version is B. And 0011, that's going to be 3. And 3 in hexadecimal is just 3. So the ending answer is, if I can find my good pen, not my good pen, but the answer is actually B3. So 10110011 is the equivalent of the hexadecimal equivalent of 10110011 is B3. Okay? I feel like I'm when I talk about hexadecimal, I feel like I'm trying to play the game Battleship. B2, B3. Now IPv4 addresses are 32-bit addresses, and it is written in terms of 8 bits dot, and instead of a dot, I'll put an X right here so you can see. In another 8 bits dot, another 8 bits dot, another 8 bits. An example, of course, is 192.168.1.1. How many bits are in one IPv4 address? And that would be 32 bits. 32 bits are in one IPv4 address. IPv6 is another story. Okay. Anyways, IPv4 breakdown. We have 192 this is how your computer sees IPv4. Sees it with by looking at this. It sees it by looking at this. It sees this, and it sees this. Okay, so we already know the binary value of 10 because all we have to do is look at our trusty numbers right here, and we have 8 is less than 10 by a remainder of 2, so that's a 1, and that's going to be 0, and that's going to be this, and it's going to be that. So that is the number 2 in binary right there, and that should answer your question. Now, the other aspect of this is your IPv4 is broken down into classes, so we can see that the first octet is known. I should have put the classes on here. That's class A. When the first octet starts with .1 and it goes all the way to .126, and we have class B, and that's going to be 127 to 191, and this is class C, which is 192 all the way to 223. The subnet masks that are associated, the default subnet mask, and I should say default, and I'll do that later. I'll put the word default, and I can do it now, I suppose. Well, the default subnet mask is going to be /8, and that's going to be 255.0.0.0. /16, that's going to be 255.255.0.0, and 20/24 is three 255s, and that's because there are each 255 represents 1, so there's 24 ones here, there's 16 ones here, and there is 8 ones here. Now keep in mind, your computer doesn't see it in decimal. Your computer sees this. Your computer would actually sees and recognizes this, and the whole important of the first octets is the first bit is always 0. So if, for example, this first octet started with 0, we know your computer would know that your IP address is a class A. Now, this is all good, but it doesn't make any sense for us to even look at this unless we want to examine artifacts. How does this affect our ability to hunt malware, or at least see what the effect of malware is in case it makes things like requests? And we can start by running Wireshark, on the network requests that are going on in the background, because that's one thing that malware can do. It can make our computer make requests on the network. So the first thing we have to do is we have to install Wireshark. Okay, and here's the basic instructions of installing Wireshark. And here is how Wireshark actually looks. Okay, and for example, we can see that we can filter for http.requests or http responses, and we can see, for example, we can click on this line item where it says HTTP protocol, and we can see all of the information. And this is the beauty of Wireshark and the beauty of knowing the OSI model, or in this case the TCP/IP model. We can literally match the output of the TCP/IP model to the output of Wireshark in terms of layers. What we're looking at here is the top layer, layer 7 through layer 4, or layer 7 through layer 7, 6, and 5. Okay, so this is the top layer. This is the next layer. This is layer 3. This is layer 2. And then this would be the physical layer. Okay, so this is layer 7. And we can see it's using Hypertext Transfer Protocol. And we can see information about the host. We can see the request method. We can see the UR, Uniform Resource Information, right here. And we can see the version, HTTP 1.1. We can see information about the user agent. Okay. We can see, all kinds of things about the accept encoding. Okay. We can see, in different pieces of information. Okay. So we should have information enough from that picture, from that image, to answer these different questions. Okay, so the idea is binary is the lowest level of representation, of how computers actually think and what triggers them. And hexadecimal is nothing more than a more suitable representation of those binaries, because if binaries is base 2, hexadecimal is base 16, so it just one character gives us more information than just a binary 0, 0, and 1. Now, IPv4 is expressed in decimal, so when we run Wireshark as a network analyzer, we can better see in human form what is going on. Okay, so this should give you the basis of your assignment today.